Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
That's adorable, and that's us. Hi, I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a good friend to the universe, I think.
You're a very good friend.
Thank you.
I'm Corinne Caputo. I'm a writer and a funny person and a friend to the universe. And I'm also a twin. And we are at Target Field. I think that's the name of it. The home of the Minnesota Twins, a baseball stadium.
Yay.
Which thematically fits for today. You'll find out why.
It does. Corinne, do you frequent many baseball games?
Okay, I'm not a baseball person. Or I'm not a baseball person. My husband is obsessed with baseball. It is a huge part of my life, even though I've never invited it into my life.
You're unwillingly a part of baseball.
I love thematically a baseball game. Like, I'm getting a hot dog and a soda and an ice cream and a little hat. Mm-hmm. I don't love how often it's happening. I think we could use less baseball games. It's always on.
Always.
He's always fiddling with something on his fantasy team. But
it blows my mind how long the baseball season is. It seems like
it's
is always
so long.
In season.
And he was just saying the other day that he's just so happy it's baseball season. And I'm like, it's always baseball season. We get
so
off
those,
for like the holidays.
Yeah, I was like, during those 2 months, is he just miserable?
And he he goes to spring training every year.
He's really into it.
He's really into it. And I remember, I always think of this article I read probably 10 years ago that was talking about baseball. And they said that the game has changed so little from its inception that every game is basically a historical reenactment. I think that's so funny. And I think of that all the time.
It's good to have a fossil sport.
Yes, 100%.
One that teaches us how things used to be. But we are here on the home field of the twins because we're talking about twin telescopes. We're talking specifically about the pair of Gemini telescopes, which people call one observatory, two telescopes, because it's the Gemini Observatory, but it is split into the north and south hemispheres. So we're gonna talk about those telescopes and some things that they found. And I do have a fun little game for you at the end, Corinne.
Oh, yay!
Yay! So normally when we're doing these observatory episodes, I start with how someone planned the observatory and how they proposed it and got funding, and if there was any drama during the attempted construction of that telescope. And Corinne, I could not find any information about the inception of the Gemini Observatory, and it actually made me pretty emotional when I was doing the research, like in a bad way. I was like, am I just not good at searching for things? Like, what secrecy is going on in the Gemini Observatory that they don't want us to know this history?
It's just buried.
Yeah, it is. And so if anyone else can find the information, please send it my way. I don't even know who the first person to propose it was. Usually I can find that information. But I will say that I spent a lot of time on the Gemini Observatory website today, and no shade. Or maybe,
or maybe shade.
I'll do shade, but it is one of the worst observatory websites that I have seen yet while doing research for this show.
That is sad to hear.
Yeah, it has so little information. The organization of the website is silly. The documentation, not there. It's
I think
wild.
I'm on the site right now, and this is really not set up in an aesthetically pleasing way.
Mm-hmm.
Oh my gosh.
When you go to the About page, usually they have information about the observatory and how the telescope works and what cool things they've discovered recently. No. They do not have that on the About page. So I don't have much history information for you about the observatory, but here's what I do know. I do know that the idea of twin telescopes didn't start with the Gemini Observatory. The National Radio Astronomy Observatory, which we have talked about because I am a radio astronomy fan, they had twin antennae in the 50s at Green Bank Observatory, which we've talked about, the Green Bank telescope. There's also something called the Keck Observatory, Keck. Maybe we'll do an episode about that one day. They are two twin telescopes. They're almost identical on top of Mauna Kea in Hawaii, but they are right next to each other. I think that Gemini is unique as a pair of telescopes in that the twins are separated, which you as a twin might have an opinion
It's just like me and my brother living states apart.
Yes. Yes, it is. So the Gemini North Telescope is also on Mauna Kea with Keck. We, for sure, are going to do an episode about Mauna Kea and especially the 30-meter telescope conflict and how that is a giant telescope they're trying to build on top of this mountain that I personally believe should not be there. But there are like 13 other telescopes already on top of Mauna Kea, including Keck and Gemini North.
That's a lot of telescopes up there.
It is. And people say that it's because it's one of the best places in the northern hemisphere to observe. The top of Mauna Kea is 14,000 feet, almost 14,000 feet above sea level. So you're high enough in the atmosphere that you're not dealing with a lot of water vapor and you don't have to see through much of the atmosphere to get to space. And they have the infrastructure there because there are already so many telescopes. So that's why they keep building more. But Mauna Kea is a sacred mountain to Hawaiians, and we should not be putting scientific instruments from different countries on top of sacred mountains in sovereign nations, which Hawaii was. Getting back to to Gemini, because I
agree.
If I let myself go, I will stand on that soapbox for a very long time. But Mauna Kea has a lot of telescopes on it, including Gemini North. Gemini South is on Cerro Pachon in Chile, which is about 9,000 feet above sea level. And I've been to both telescopes. Yay! Not at the same time, obviously.
Well, maybe 1 foot on each.
I think I calculated it, the distance between Gemini North and Gemini South. They're something like 7,000 miles apart. So sure, one of my legs
Easy.
is 3,500 miles long.
A disaster has happened if that's what you did.
I am a very leggy person. Like, for my height, I have very little torso and mostly leg.
Mostly leg.
Mm-hmm. So when I'm sitting, people think I'm much shorter than I am.
Oh, interesting.
But it's really good that they have these telescopes in these two different locations, these identical telescopes in two different locations, because it lets them see basically the entire sky. And because the telescopes are basically identical, you know that you're getting like the same type of data from both parts of the sky with these two telescopes. It was, from its inception, this is as much as I can tell, always a big international collaboration. Different countries have come and gone from the collaboration, but it is currently owned and operated by the National Science Foundation. They provide about 70% of the funds and resources to operate Gemini. But it also is a collaboration with the National Research Council of Canada, CONACYT of Chile, which makes sense because one of the telescopes is in Chile. It would be very rude of us to put a telescope there and then not let them have anything to do with it. There's another agency, MCTI, in Brazil, another in Argentina, and the Korea Astronomy and Space Science Institute in the Republic of Korea are also involved. The UK and Australia used to be some of the partners, but the UK dropped out and pulled their funding in 2012, causing the observatory to really restructure things and become more efficient and reduce a lot of costs.
Wow.
And they did. They were pretty successful. 2012 was a turbulent time. I don't know how long they were planning these telescopes, but they started to break ground, at least in Chile in 1994. I think they broke ground on both telescopes around the same time. The first light for the Gemini North telescope, so the first time that it took observations, the first time light hit the telescope, that was in 1999. And then Gemini South had its first light about a year later, in 2000. The mirrors for these telescopes, they were constructed in Corning. Do you know about Corning, Corinne, as a New Yorker? I only heard about it a few weeks ago. One of my coworkers was going to tour some glass factories up in Corning and do glass antique shopping up in Corning. Apparently, it's a place in upstate New York that is well known for good glass making.
Oh, so they were. Well, I know Corning ware, but I don't think that has to do with Corning.
Maybe
it does. It's ceramic, I guess.
Then maybe not, because I think they specialize in glass. But it was, the mirrors were constructed in a Corning factory in upstate New York, and then they were transported to Paris to be ground and polished. And then from Paris, they were sent to their destinations in Hawaii and Chile to be put on the telescopes, I guess.
I mean, if you're making it to Hawaii, then what's one more trip in there? But I'm like, that feels like a dangerous risk to like create this mirror and then send it abroad.
Yes. Send it east across the Atlantic when it has to end up going back, like across the Pacific.
Wow. I'm just so impressed by things we have in place that ship items around the world.
Yeah. When you start thinking about it, it really does boggle the mind that anything works at all.
I know.
Corinne, how much do you think it costs to build these 2 telescopes?
Oh my gosh. So much money.
Yeah. Around like late 1990s.
Like $200 million.
Corinne, why are you so good at this game?
Was I right? Because I almost said $1 billion.
It was $184 million.
I was like, let me be a little bit. To me, anything over, I don't know, $100,000 is millions. So like...
Yeah. You have such good intuition.
All right, we'll see if that holds up.
I'm keeping track. $184 million to build these 2 telescopes and ship them around the world on these multiple legs. But let's get into like what the telescopes are actually doing and some numbies, some telescope specs, if you will. Both of these telescopes, they are identical. They are 8.1 meters in diameter. Like the mirrors are 8.1 meters across. That's more than 26 feet.
Oh, that's actually smaller than I was going to say.
Really?
I don't know why I thought it would be like just dwarf me completely.
Well, I mean, this is 5 me's across.
Yeah, that is a lot
5
of me's.
Moiyas could lay across.
Well, as we're learning, my sense of scale is not right.
Except for money.
I need a quarter. I need a quarter for scale for everything I talk about or think about.
I guess you could use a quarter for scale for one of the Gemini telescopes. I don't know how helpful it would be here. But yeah, they're 26 feet across. They are about 8 inches thick, 20 centimeters thick. And they are not designed to maintain their shape on their own. They need help to make sure that they stay in the perfect position to actually get clear images and data. So they have 120 something called actuators. These are tiny little machines that gently nudge the mirrors back into position to get that perfect form. And the adjustments that the actuators make are moving the mirror by 1/1000th the thickness of a human hair.
Oh my gosh.
Yeah.
That's so small. The
margins are tiny. You don't need a quarter for that scale.
That I get.
Yeah, these measurements have to be really precise. So we have to make sure that the mirror looks exactly the same.
Yeah.
And that's why we had to send it to apparently a fancy Paris company to grind and polish it to get as flat as it could be. The mirrors alone, each mirror weighs 22 tons.
Very heavy.
It's very heavy. And then those mirrors are put into bigger machines to hold them and to move them. So how much do you think like one Gemini telescope, not just the mirror, but a telescope weighs?
Whoa. In tons?
In tons.
Like 100.
Haha, no.
She got me.
Got you. 380 tons each.
Wow.
I don't even know how to fathom that.
Okay, I'm actually looking at a converter for pounds for my American brain. 760,000 pounds.
Yeah, for one of the telescopes.
750,000 pounds.
But they sit on this foundation that has oil bearings, so it's little tiny metal balls on top of a very thin layer of oil, so the telescope can actually be moved by a single person.
That's crazy. That feels like magic.
It is magic. You know, Arthur Clarke said that any sufficiently advanced technology is indistinguishable from magic, and I think moving a Gemini telescope by yourself counts as magic. The telescope observes in the optical to mid-infrared wavelengths. So I'm going to tell you in a little bit about the different instruments on the telescope and what wavelengths they in particular observe. But it's like, I don't know, a couple hundred nanometers to maybe like 2 micrometers. So it's a pretty narrow range, but it does give us a good view of the infrared and the optical. And when we are observing in the infrared, that lets us see through a lot of dust. out in space. So with Gemini being able to see through a lot of dust, we can see things like star and planet formation because a lot of material just gets ejected in those events. And you can see objects or events towards the center of the galaxy because there's a lot of dust and gas getting in our way there. And you can also look kind of through all of the clouds of dust that surround black holes. So they've also done some pretty good studies of big black holes in other galaxies. One thing that makes these telescopes so effective, I guess I'll say, is that they use a kind of technology or a type of process called adaptive optics. Have you ever heard of this?
No, I haven't.
Based on the name, what would you think adaptive optics would do?
Something about like if the environment changes or like what it's doing changes, it can like on its own readjust.
Yes.
Great.
Yes. This is an example of an aptly named process in astronomy. There aren't many
Finally.
of those. So adaptive optics apparently was first proposed by an astronomer named Horace Babcock. Great name.
Great name.
In 1953, so more than 70 years ago. And it was developed, unfortunately, by the Defense Advanced Research Projects Administration, or DARPA, in the 70s. And sometime in the 80s, a few different telescope groups, like a few different observatories, tried to incorporate adaptive optics into their function. And they found that it actually does really cool stuff. So light waves, when they come through our atmosphere, they get distorted. The photons of the light wave, maybe they get scattered by different molecules in the atmosphere. Usually water vapor is getting in the way, or wind can move things. The atmosphere isn't like the same everywhere. So in some places it's a little bit more dense, or it might be a little bit cooler or hotter. And so these density and temperature distortions can affect the image that you get when you're looking through the atmosphere. So adaptive optics is a technique to remove those distortions. And there are a couple different ways you can do it, I think, but Gemini essentially shines a really powerful laser into the sky. And if you Google like Gemini observatory laser adaptive optics or whatever, you can see a picture of this really bright laser coming out. Like, I wonder if they have to tell airlines or something that the laser is out there, because I feel like it would affect vision of pilots.
Yeah,
but
sure.
They shine the laser and they measure how the laser beam is affected by the atmosphere, because they know the laser beam really well. They know how it should look. So as they see it getting batted around in the atmosphere, they can essentially come up with like an equation to describe the types of distortion. And then when they take their observations, they can remove that distortion from the image.
Okay.
And like you said, they have to be really adaptive to changing environments. So that's the point here. It's not that like they shine the laser on the first of the month and then they use that equation to remove all images for that month. Like there's an instrument that is always doing adaptive optics, pretty much.
Cool.
So let's get into the instruments. They change over time. So these are the instruments that are on there now.
Okay.
They're also changing their adaptive optics instruments, or they did like right at the beginning of last year. So they're dynamic. They are making progress. Let's do the Gemini South instruments first. So one of the instruments is called the Gemini Multi-Object Spectrograph, or GMOS, G-M-O-S. It observes from 360 to 1,030 nanometers. So that's like in the optical, 360 nanometers is like a little bit less than red, right? Doesn't red start around 400 nanometers? Maybe it's the other way around. No, like 600 nanometers is red. Yeah. And then 300 would be like near violet.
I have no idea.
So this goes from the optical into the infrared, which is about 1,000 nanometers. The GMOS instrument takes both images and spectra, so it's a double threat. And the enclosure that this instrument is in, they have a picture on their website with a human to scale. So
that I love.
Yes,
I love that.
That was helpful. They didn't tell me anything about that human, and it was just like an outline, so I don't even know if they were trying to say
the
like
average
this is
person.
Right. Is this the average person, the average man, the average what? Like, I don't know.
Yeah.
But roughly human-sized. That's how big this instrument is.
Love it.
Mm-hmm. They also have an instrument called GHOST.
Yay!
Yay! It's an acronym. It stands for Gemini High Resolution Optical Spectrograph, where both the S and the T are capitalized.
Sure.
I hate it. This
you
is
hate the
high...
tool, or you hate the acronym?
I hate when we use a letter in the middle of the word to make an acronym work.
I get it.
Like, I respect the hustle, I guess, but just be a little more creative. This is a high-resolution spectrograph, and it can take a spectra of 2 objects at once. Ooh. Which is exciting. And it observes around the same wavelength range, 380 to 1,000 nanometers. Actually, they say 383 nanometers to 1,000. Gotta be precise. There's an instrument called Flamingos 2. I don't know what happened to Flamingos 1. Or if there was a Flamingos 1. I hope so. But wouldn't it be so rowdy of them to just start with 2?
Definitely.
It is a near-infrared spectrograph, and it observes it from 1 micron to 2.4 microns. Microns are 1,000 times bigger than nanometers.
Okay.
Because a nanometer is 10 to the negative 9 meters, and a micron is 10 to the negative 6 meters.
I understand that logically.
Yes.
And I have no...
Let me say it another way.
I have no quarter for scale.
We would have to cut the quarters so tiny.
Yeah, compare that to a quarter for me.
So 1 micron is 1 millionth of a meter, and 1 nanometer is 1 billionth of a meter.
Wow, tiny.
Mm-hmm. Very small. Yeah, that quarter, that ain't doing nothing. That's not helping you at all. Gemini South also has an instrument that works closely with their adaptive optics. They have the Gemini South Adaptive Optics Imager, and it gives really crisp images in the 1 to 2.5 micron range. And then it has 2 visiting instruments, so ones that are more temporary. The first is called Zorro.
I watched that.
You watched? How recently?
Oh, not since I was a child.
Oh, okay, yeah. It's been a while for me, too. We can't watch that for Pale Blue Pod.
I was going to say,
yeah.
I don't think we can go back.
No, maybe I'll just watch it on my own. So Zorro is an optical imager, and then iGrins is an immersion grating infrared spectrometer, and there's a lot of nested letters in that. But it is a high-resolution near-infrared spectrograph. So those are all the instruments on Gemini South. Gemini North also has that GMOS instrument, the multi-object spectrograph, that looks as big as a person. And Gemini North also has a near-infrared spectrograph that covers 1 to 5.5 microns. So that's a much larger range than the instruments in the South. They have a near-infrared imager that has 3 different cameras and covers, again, 1 to 5 microns. And then they have 2 visiting or more temporary instruments. One is called Alopeke, which is a Hawaiian word. It means fox, and it's an optical imager. And then they have one called Maroon X. And I wish so much that it had been Maroon V for Maroon 5.
Oh my gosh, you're so right.
They missed an opportunity.
Flop.
It is a high-precision spectrograph designed to study exoplanet atmospheres. So this observatory can study anything from exoplanet atmospheres up in scale to star formation to galaxy mergers and black holes. So it really runs the whole gamut, which is nice.
Hi, it's Corinne. This is a huge thank you, as always, to our patrons who support the show every month, to our Sun-like stars, Lissa, Scott Reynolds, Ian O'Leary, Augustin, Tom T. And you can support us, hear your name on the show, make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. If you sign up for an annual membership, you get a 13% discount. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod. And if you can't support us financially, we still love you so much. You can support the show by reviewing it on whatever app you use and sharing it with your friends. Dear cat parents, we know you're obsessed with your cat. Admit it, if we looked at your camera roll right now, it would be 90% pictures of your cat. You give them the best. But if you're honest, you might struggle to keep their litter box clean. Have you heard of Litter Robot? Litter Robot is the solution to all of your litter box problems. Never scoop again with LitterBot. LitterBot's self-cleaning technology automatically cleans after every use, so your cats will always have a fresh bed of litter to do their business. And best of all, your friends won't think your house smells like a litter box. That's amazing. Litterbox will even send a notification to your phone when it needs to be emptied, and it gives you data and insights to stay on top of your cat's health. Join over 1 million happy pets and pet parents who've upgraded to Litter Robot. What are you waiting for? And as a special offer to listeners of this show, you can go to stopscooping.com/palebluepod and enter code palebluepod to save an extra $50 on any Litter Robot bundle. That's an extra $50 on any Litter Robot bundle at stopscooping.com/palebluepod and enter code palebluepod at checkout. Stopscooping.com/palebluepod and enter promo code palebluepod. And before you go, if you are loving Pale Blue Pod, and especially if you're loving Dr. Moiya McTier, you have to give our other podcast, Exolore, a listen. If you don't know, Moiya is a folklorist as well. So if you've ever wondered about what life would be like on different planets or how writers create your favorite fictional worlds, Moiya has the facts. On Exolore, Dr. Moiya McTier explores fictional worlds by building them with a panel of expert guests, interviewing professional world builders, and reviewing the merits of the worlds that have already been built. You're going to laugh and learn and love, and you'll gain an appreciation for how special our planet really is. Subscribe today by searching Exolore on your podcast app or by going to exolorepod.com. Okay, back to the show.
I'd say the best part of the Gemini Observatory's website was the page that tells you how to propose for time on the telescope. That was very clear, and it starts with it literally just says start here at the top of the page and then walks you through the steps to propose an observation. So I really appreciate that. Gemini was also one of the first observatories to start using a queuing system in their scheduling. So typically, I guess before that, you would have had to propose an observation that happened at a specific time, looking at a specific target, or you could propose a survey or something. But the queuing scheduling system lets you propose an observation that doesn't have to happen at a specific time, and then the observatory can slot it in wherever it would best work.
Sure. That's great.
Yeah, so they can base it off of what's in the sky right now, what's the weather like, how dark is it, things like that.
And it optimizes the use of the telescope.
Exactly. Yeah, which might have been, I don't know if they were using the queuing system all the way at the beginning or if they started doing it after the UK pulled their funding and they had to cut down costs.
Sure.
But it is pretty effective at cutting down costs. Another thing they did was make the telescopes remote operated. So instead of having to be up on the top of the mountain to manually operate any of the telescopes, you operate them remotely from the bases of those mountains.
Oh, nice.
Yeah, the dorms or whatever that they have at these observatories are nice. They usually have a cafeteria, places to sleep, a little rec room or something.
Oh, I love it. Do the operators, is it full time? Are they there year round?
I don't know. Maybe not.
Maybe not. I'm picturing them like lighthouse keepers.
I think it's less like that. My impression of lighthouse keepers is that it's one person per lighthouse.
Yes,
they live
exactly.
There. The telescope operators, it's a
more
job.
Social. Yeah.
But because these telescopes are in more remote locations, it's probably more convenient for them to have maybe a week or two on and then some time off. But I don't know. I'm just speculating. But yeah, I didn't stay in the dorms on Mauna Kea. We were staying further down the mountain and then going up. But we did stay in the dorms around the Gemini South telescope on Cerro Pachon, and it was cute. I had my own room with my own little bathroom. Yeah,
I love it.
Very, very 80s aesthetics, which is these telescopes are not built in the 80s, but the dorms have definite 80s aesthetics. So here's how you propose. Here's the process for getting an observation on Gemini. The scientists will figure out what they want to see. They will propose an observation. Like there's a website where you can download templates and then you can upload your information for Gemini. But there are 5 different classes of observation that you can choose from. And these range in terms of like how complicated the project is and how long it will take to do the observation. So the lowest class is called the fast turnaround class. And these are for short projects that can be slotted into the queue whenever the conditions are right, usually for about 3 months at a time. So you propose this and then sometime in the next 3 months, your observation will be done. There's a deadline for this type of proposal at the end of every month. So throughout the year, you can start proposing these fast turnaround projects. And then they have standard semester projects, which is a similar concept, but it's for projects that will take about 6 months to observe. You can be slotted into the queue, or you can request a specific observing time. So you have more options. There are 2 proposal deadlines each year, one at the end of September and one at the end of March. So we've just missed the call for the B round of deadlines. Then there are large and long programs. These are bigger projects that will take a lot of observing time, like more than 50 hours of time on the telescope. So they can be doing this research over a year or 2 because it can take that long to get that much time on the telescope. There's only one deadline for this. It's at the end of March. So only once per year can you submit a proposal for one of these large and long programs. And then there's director's discretionary time, which we have talked about before. Other telescopes have this. The Hubble Deep Field Image was done using a Hubble director's discretionary time. So the director of Gemini can just like, I said he. That's bad on me. The director is currently a man, but the last director was a woman. But the director has a certain amount of time set aside each semester to just use the telescope however they want. Not however they want, but within reason.
Yeah.
And then there's a class of observations called poor weather observations. So these proposals can come in literally at any time, and they are for observations that can be done even like, I don't know, when it's raining, when it's cloudy, when it's a full moon, so there's a lot of ambient light in the sky. I don't know what type of thing you would propose for this, but it's an option you have. Because weather's always getting in the way. So once you submit your proposal, the proposal is reviewed by a time allocation committee, this group of people who decide what is a good enough proposal to get time and how will they schedule those observations. I think Gemini is oversubscribed. It gets more proposals than it can actually do observations for. I want to say their oversubscription rate is like they get to do 80% of the proposals that they get.
That feels good.
So, yeah, it feels pretty good. Once the observation is done, the data is collected and then reduced in a pipeline before it gets sent to the scientists to do their data analysis. And I think you can also get the raw data, but you want their pipeline because they know their telescope best and they know how their telescope is going to affect the data so they can remove those effects. There is a Gemini observing game. They give you instructions for making a deck of cards, or you can play the game online. The link to that is in the research notes for our patrons. The game takes you through the steps of planning and then doing an observation, but you can get clouded out, or I think maybe the telescope can break down or something.
That's so fun. So simple and fun.
I
just
know.
Cosplaying.
Yes, just cosplaying being an astronomer.
Yeah.
So it's free, everyone. I recommend it. I think I'm going to try and play this sometime soon. The Gemini Observatory is overseen by an international board of directors from the countries that are part of the collaboration, and operation and management is run by Noir Lab, which is owned by the National Science Foundation. So they are still in charge at the NSF, but they have these little subsidiaries that will actually operate things for them. Any questions about the telescope and how it works and how it's run before we get into some of its discoveries?
I mean, my big question was how likely you are to get, your project accepted. So I love hearing that 80% feels good.
Yeah.
I think I'm in a college acceptance rate mindset of or even just a job application thing where it's you're never going to hear from them.
Yeah, it is nice because there are some telescopes that are more oversubscribed. I don't know if there are any telescopes that are like, hey, please submit more proposals.
Yeah. We want to do more fun things.
Yeah, but this is a good middle ground.
Sure.
I have 4 cool discoveries for you. I went on the press release page for the observatory and picked the 4 recent, most interesting sounding articles.
Ooh, yay.
In my opinion. So the first has to do with merging black holes. Did you know that black holes merged and collided?
I did know that, and I find that kind of scary.
Yeah. The scariest thing to me, although I'm not scared by it, but the scariest thing to me about this is that we know black holes must merge because we think that's how we get the supermassive black holes at the center of galaxies, but we've never directly observed a black hole merger. Okay. We've tried. We've seen black holes and neutron stars. We've seen 2 neutron stars merge, but we've never directly observed 2 black holes merging. But recently, like in the last year or so, archival data from the Gemini North telescope was used to measure the masses of a binary black hole pair in an elliptical galaxy called B2-0402 plus 379.
Classic
Beautiful name. This is the only supermassive black hole binary pair ever resolved in enough detail to see both objects separately. Usually we see them just as like one little blob, like we can't tell them apart, but we can tell them apart. And it also holds the record for having the smallest separation ever measured. These 2 black holes are only 24 light years away from each other, which is very, very close.
Yeah.
Our galaxy is 100,000 light years across. So these black holes, they're right next to each other. But it seems that they have been at that distance for about 3 billion years.
Okay.
There is something in astronomy called the final parsec problem, where we have wondered for a long time how, especially black holes, but other massive objects, how they eventually come together, how they bridge that last gap of about a parsec, which is like 3 and change light years. But they were looking at this system, this very close together system, and they were trying to measure its mass by looking at the motion of stars around these 2 black holes. And what they found was that the pair together, in total, weighs about 28 billion solar masses.
Heavy.
Very heavy. The supermassive black hole at the center of our galaxy, Sagittarius A star, is only 4 million times the mass of our sun. Each of these black holes is 14 billion times the mass of our sun.
Oh my gosh.
Yes, quite large. Quite large. And it makes sense to a lot of researchers that they have been stuck at that 24 light year distance for like 3 billion years, because previous hypotheses about this final parsec problem and about big things merging says that it takes heavier black hole pairs longer to merge than less massive black hole pairs. And that might be kind of counterintuitive to a lot of people. But when you get these very massive objects orbiting each other and spiraling in towards each other, they fling out other things through gravitational interactions. So if there's any stars or gas or dust in the vicinity, the spiraling of these objects causes them to fling away from the system. But those things that are around, the stars, the gas, the dust, by interacting with them, that causes dynamical friction and makes the black holes slow down, so they start getting closer together. So these more massive objects, they fling more material away from them, and then they don't have anything to help them slow down. So that seems to be what's happening here. And I thought that was fun, that we found the biggest black hole binary pair in history. Gemini South data was recently used to find the origin of a long gamma ray burst. This was in 2019. And they saw a new way. It had been long hypothesized, but this was the first time seeing this. They discovered a new way for stars to die.
How fun.
Yay.
Tragic fun.
I'm pretty sure that we covered different types of stellar evolution in our star types episode. So stars will end their lives as white dwarfs, or they'll go supernova and they'll become neutron stars or black holes. Those seem to be like the options for a star. Mm-hmm. But there's a secret fourth option. So in 2019... Data from the Gemini South telescope was used to kind of look back at this gamma ray burst that had been discovered with a different telescope. But usually gamma ray bursts are very short-lived, like a couple seconds, maybe a day. This gamma ray burst lasted longer than most other gamma ray bursts, and it was pretty intense. So what they found was a bunch of stars around a black hole were moving because they were affected by the gravity of the black hole. And there were enough stars, and they were moving fast enough that some of the stars collided with each other, which doesn't happen out in space. It doesn't happen in the fields of galaxies because stars are too far apart. But around really gravitationally powerful black holes, you can get stars that collide, and then they give off these very energetic gamma ray bursts.
It's probably gorgeous.
Probably. Yeah, I'd love to see a picture of that. But it was a really old galaxy that wasn't forming new stars, so they could see it really clearly because there weren't like bursts of star formation happening in other parts of the galaxy.
Cool.
Now we're going back to Gemini North and a discovery that they made with their Maroon X instrument, which is unfortunately not named Maroon
titled.
5. Really missed a great opportunity. But with this Maroon X instrument, Gemini North found, quote, rock-forming elements, unquote, in the atmosphere of a hot Jupiter called WASP 76b. This is a pretty well-studied hot Jupiter. We've known about it for a couple decades now. And it is 12 times closer to its star than Mercury is to our sun. It is
close.
Very close. Temperatures there probably reach 2,000 degrees Celsius.
Oh my
Very
gosh.
hot. All of that heat makes the planet puffy. Like, it physically makes the planet have more volume because the elements, the gas, gets expanded from the heat. And also, they believe that all of that heat evaporated these rock-forming elements that could have been in the core and then dispersed them throughout the atmosphere. And those elements, I have a list here: sodium, potassium, lithium, nickel, manganese. I love manganese for some reason. Chromium, magnesium, vanadium, barium, calcium, and, as previously detected in the atmosphere of WASP 76b, iron. A few years ago, they found that it might rain iron on this planet.
Wow.
And so by looking at the spectra, so they took spectra of this planet's atmosphere and studied all the different elements that were there, and compared that to what we know about Jupiter in our system, what we know about star and planet formation in general, and the levels of heavier elements in this hot Jupiter indicate that gas giant planets may form more like stars than like rocky planets. So we know that rocky planets form by as the disk of junk around a newly formed star keeps orbiting, eventually collisions will happen and you'll get like a snowball effect of little pebbles getting bigger over time through collisions. That's how rocky planets form, but this finding seems to imply that perhaps gas giants form more by gas kind of like collapsing in on itself in the protoplanetary disk. So maybe what I've been teaching about planet formation is not right, but we've known for a long time that our models of planet formation need work. Like, we are actively trying to figure out how different types of planets form and if they migrate throughout their systems. Okay, I have one more finding for you. This is from the Gemini South Adaptive Optics Instrument, and that data showed us the first evidence of a dying star that was similar to our sun engulfing an exoplanet. This is important because we know that the sun in about 5 billion years is going to puff up into its red giant phase, and it's going to definitely engulf Mercury and Venus, and we think it will probably engulf Earth too, but we're not sure. So seeing events like this out in space will give us more of a clue of what to expect here. Which is really exciting.
I'm loving that you're using the word puffy. This is making the universe feel quite cute, despite any of the scary stuff going on. Dead stars, dead planets.
It's puffy. So they studied this star. It's in the Milky Way. It's only about 13,000 light years away from us. And it emitted an outburst of long and low energy. So a long burst of like low power energy. And what they found was that this system had ejected a bunch of material, 33 Earth masses of hydrogen, and a third of an Earth mass of dust when the planet was engulfed. And by studying the mass of stuff that was ejected from the system, they were able to estimate the mass of the star and the planet that got engulfed. The star was between 0.8 and 1.5 times the mass of our sun, so pretty sun-like. And the planet was more of a Jupiter, between 1 and 10 times the mass of Jupiter. And it's really cool to see a planet get eaten by a star.
Yeah, I'm sure. For some.
For some. Probably not the planet. Probably not anyone living on that planet.
R.I.P.
R.I.P.
I think that's really cool. I love that we've seen things we never thought we could see or would see, and now we have.
Now we have, yay. In that case, I have a little activity for the both of us. So this telescope is named Gemini after the constellation of the twins with Castor and Pollux. And I am curious what we think telescopes or observatories named after other zodiac signs would be like.
Ooh.
We're not going to go through all of them, but I have a list here, and if anything comes to mind, please let me know. But I did think that for Libra, because Libra is the scales, right? It's all about balance. I imagined that Libra is like a wide wavelength telescope on the ground at the equator. And it is on a mission to scan the whole sky, but it's trying to keep everything balanced. So it scans like a patch of sky in the northern hemisphere and then goes down to the southern hemisphere. Yeah, it bounces back and forth so that neither hemisphere feels excluded.
It's all 1-to-1.
Yeah. And of course it does that at every wavelength too, like at every bandpass.
I love that.
Just to keep everything even.
I love that. I am thinking that like a Taurus, because they're kind of like reliable and like value quality over quantity. Maybe it might not be like the most cutting edge thing, but it's like the reliable, true equipment that we know we can trust. And it like, maybe it looks at like one thing for a really long time.
Oh, it's making me think of like Arecibo. Like, it's just a real big, sturdy telescope that can't move. It just looks up above
Reliable, and that's what it's supposed to be. Resistant to change.
Until it wasn't.
Well, that's why we have our new Taurus telescope.
The new Taurus telescope, yes. Watch out, Puerto Rico. We're going to do an episode about Arecibo at some point. Okay, do I have any of this? I think Aquarius might be not a telescope, but like a rover or something.
Ooh,
like an instrument that we send to another world to look for water, because Aquarius is the cup bearer.
Yes.
So maybe it's a little rover that we send to maybe the moon, maybe Venus, or like I don't know. Maybe it's one that goes to all of them.
That I think an Aquarius would want to do.
Yeah.
I'm trying to think, all my Virgo friends are like the most organized people I've ever met. They're just like really paying attention to detail and striving for like excellence and like optimizing their life. Not in like a crazy way, but like in a spreadsheet way.
Oh, I love that. Okay, then how about we make the Virgo telescope something that is extremely high resolution? Oh, maybe it's an interferometer. Maybe it's an array of telescopes working together so they can get extremely high precision images, high resolution images. And it's a survey mission. So instead of people applying for time, proposing observations, it has it all planned out and it knows what it's going to do for like a whole 4-year stretch of time.
That's exactly it. That's right.
I love this. NSF, get at us.
Yes. Do you need me to just pitch ideas for large, expensive projects?
All right. I didn't think of it. Nothing came to mind for any of the other signs, so that's all I had.
You know, it'll come when it comes.
You're right. And listeners, if you want to create observatories or telescopes based on your sign, please let us know. Please reach out. We are PALEBLUEPOD on Instagram.
On everything.
Yeah. All right. Well, It doesn't matter if you're a twin or not, listeners, because I am not, and Corinne is, and we are both still space, and so are you.
There's two types of people.
There's two types of people in this world. You're either a twin or you're not, but it doesn't matter.
But we're all space.
We're all space. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.